In these videos, I'm going to be working through the solutions of week 3 homework. The first part of the week 3 homework had to do with sets, and most of the questions dealt with Venn diagrams. So this first question, we're trying to complete Venn diagrams for both of the sets presented to determine if the sets are equal. Go ahead and look at A minus B minus C. So I want to think about what the Venn diagram of this set would look like. So I know that set subtraction just means take everything from B minus C and remove it from A. So in order to do that, I need to know what is in B minus C. So I'm just going to start by shading and understanding the regions of B minus C. B minus C takes everything in B. So if I think about what's in B, I'd have region 1, 2, 3, and 6. So those are my region labels. They don't mean elements or anything, they're just labels. So B contains 1, 2, 3, and 6. And if I remove the parts that come from C, C has regions 4, 7, 1, and 3. So if I remove the sections that C covers, I'll have 1 and 3 that I'll have to remove from C. So if I think about B minus C, I'm just going to shade it. I'll get region 2 and 6. So that's region B minus C. Now if I think about A, with region A, the regions that I would shade for A, I'd have 1, 2, 4, and 5. So if I remove B minus C, I can see from that drawing and from my work here that B minus C just contains regions 2 and 6. So if I remove the regions that B minus C has, the only thing that I'd have overlapping here would be 2. So I'd take A, which is 1, 4, 2, and 5, and remove anything that came from B and minus C. So for sure 6 isn't there because 6 isn't part of A. So if we're taking something away from A, what we have left must be in A. And then B minus C, the only thing else we have from B minus C is region 2. So we also need to remove that. So A minus B minus C contains regions 1, 4, and 5. Okay. Now let's think about A minus B minus C. So first, I want to understand A minus B. So this means take everything in A, so regions 1, 2, 5, and 4, and remove parts from B. So I'd remove parts 1 and parts 2. So in A minus B lives region 4 and 5, okay? And the reason I'm doing A minus B first is because the parentheses are grouping that operation, just like the parentheses were grouping the operation B minus C here. So, so now A minus B we have 4 and 5. Now I want to remove anything that comes from C. And if I look at the Venn diagram for A minus B, which is what I've got going on here right now, the only thing that is touching C right now is region 4. So I just remove that region. So if I remove 4, the only thing I have left is 5. And so I can see that this, from this shading, right, because this is the Venn diagram for A minus B minus C, and this is the Venn diagram for A minus B minus C. So from this shading I can see that this equality is false and these sets are not equal. I could say that A minus B minus C is a subset of A minus B minus C, because the only thing shaded in A minus B quantity minus C is 5, and that's contained in this first set, A minus B minus C. So this is a subset. It could even be a proper subset because it's not equal, right? So we can call it a proper subset. All right, so let's do another one of these. A couple more Venn diagrams here. So first set we're going to try to understand is A union B intersect C. So again, the B intersect C is grouped by parentheses, so I know that I want to start there. When I think about intersection, I think about where the sets overlap. So I'm going to look at set B and set C and think about what regions they have in common. Well, the only regions they have in common are 1 and 3. So I know that in region B and C lives, in set B intersect C lives regions 1 and 3. Now, unite means take everything from both sets. So this means I'm going to take all regions from A, all regions from B intersect C. So I'm definitely going to have regions 1 and 3 shaded for my final Venn diagram, but then I'm also going to add any regions that come from A. Because A, I have 1, 2, 4, and 5. So I already did 1, so then I need to add 3. So I'm going to take all of A for sure. I'm also going to take B intersect C because I have union, so I'm taking everything in both. So I'm going to get regions 1, 2, 3, 4, 5 for my A union B intersect C. Now let's look at this other set. I've got A union B intersect A union C. So these two sets are groups, so we need to figure out the union first and then find the intersection. So let's look at A union B. This means take everything in A, take everything in B. So A union B is going to be regions 1, 2, 3, 1, 2, 3, 4, 5, and 6. And keep in mind, you don't have to label your regions in this exact order or number. It doesn't really matter. They don't even have to be numbers. They could be letters. But it's just a way of keeping track of those 8 regions and determining things about the Venn diagram. So A union C means take everything in A, take everything in C. So I'm just going to do this in a different color so we can see what's going on here a little bit better. A union C, so I'm going to take C, so region 7, 3, 1, 4, and I'm going to take A, regions 5, 2. So in A union C, I'll have 5, 2, 1, 4, 7, 3. Okay. Now I'm to take these two sets and find the intersection. So that means only take what they have in common. So if you want to do it region by region, you could just see which number appears in both of these listings, or you can do it by color here. You can kind of see where red and black is happening. So it's definitely not happening here. It's definitely not happening here. But it looks like for all the other regions, both of those colors are occurring. And let's just verify with our labels here. I know that 1 appears in both of them, so I'm going to take that to be in my regions of my final set here. So I'll have 1 and 2 occurs in both. So 1, 2, and 3 occurs in both. 3, 4 occurs in both, and 5 occurs in both. And that's it. And so I've got 1, 2, 3, 4, 5. And look, 1, 2, 3, 4, 5 over here too. So this tells me, because their Venn diagrams are the same, that these sets are equivalent. And so this is just like distribution with logical operators, when we have and across or across and. And the same thing is going to work if I have A intersect B union C. I can write this as A intersect B union A intersect C. Okay, so keep that in mind. All right, let's try another one. All right, so I have another set subtraction one, and I'm trying to determine if this equality is true or false. So I need to draw a Venn diagram of both sets to determine if the sets are the same. Now, another thing to keep in mind here, you could use the logical representation of these set operations to determine if the sets are equal. But now we're just using Venn diagrams, but kind of keep in mind that logical definition of these set operations and try to play around with it to see if you can show the set equality in that way too. But so let's look at A minus C minus B minus C. So I want to figure out, is that the same thing as A minus B? And it might kind of make sense because it looks like if we distribute the negative, we end up with negative C plus C, and then we might just end up with A minus B. But you have to be careful because these operations are a little bit different than what we're used to with just regular subtraction with real numbers. So let's look at the set on the left-hand side first. So let's figure out which regions we would shade for that. So let's go ahead and just shade in A minus C and see what's happening there. So A minus C, it says just take everything in A but nothing in C. So the only thing left would be regions 5 and 2. So A minus C has regions 5 and 2. Okay, now I'll do it in another color here. Let's look at B minus C. That means take everything in B but nothing in C. So if I take everything in B but nothing in C, I'll just have regions 6 and 2. Okay. Now I'm taking A minus C and I'm subtracting B minus C. So this means remove any regions of B minus C that overlap in A minus C. So the only region that's doing this is 2. So this means remove 2 from A minus C. So you'll remove this overlap here. And 6 was never in A minus C to start, so nothing happens if I do that. And so I'm just left with region 5. Okay. Now if I'm looking at A minus B, this means take everything in A but not in B. So this would just be regions 4 and 5. So these are definitely not equal. I know that A minus C minus B minus C is a subset of A minus B, but they're definitely not equal. Over here I've got regions 4 and 5. Over here I do not, right? Because region 4 was taken out because I took it out from A minus C, you know? B minus C. Yeah. So I would say this is false. And the proof would be in the Venn diagram of those two sets. Okay, actually we just talked about this. We talked about this distribution. So we're going to prove this equality with Venn diagrams. So let's look at A intersect B union C. So B union C means take everything in B, take everything in C. So with B I have regions 1, 2, 3, and 6. With C I have regions 1, 3, 4, and 7. So I have to add 4 and 7. So take everything in B, take everything in C, that will be B union C. And notice I'm doing that first because it's grouped by parentheses. So I need to do that operation first. Now I want to intersect that set with A. So I'm going to label A here so I can see where the overlap is. So A contains regions 1, 4, 2, and 5. So A I have 1, 2, 4, and 5. And so if I see my overlap, intersect means take only what they have in common. So I've got 1 in common, 2 in common, and 4 in common. Okay. And if I look at my Venn diagram, my shading here, the only place where there's blue and green is 1, 2, and 4. Oops. So it makes sense that that would be the regions we'd get. Okay, so for this set, I have regions 1, 2, and 4. Now let's look over here at A union B intersect A union C. So I have two operations grouped by parentheses, so I'm going to figure out those two sets first. So I'm going to figure out what A union B is. This means take everything in A, 1, 2, 4, 5. Take everything in B, 1, 2, 3, 6. So I've got an A union B, I've got 1, 2, 3, 4, 5, 6. Those are the regions that I take for A union B. Now for A union C, it's a similar story. Take everything in A, take everything in C. So in A union C, I would have everything in A, so I have 1, 2, 4, and 5. Everything in C, 4, 7, 1, 3. Okay, so everything in A, 1, 2, 4, 5, and everything in C, I'll also get 3 and 7. Now, if I'm intersecting these two sets, I only want to take what's in common. If I was taking the union, then I'd get everything in green and everything in blue. But now, since I'm taking the intersection, I only want to see where there is overlap. And so, so I misspoke earlier. This is false, right? Okay, good. But let's see what they have in common. 1 is in common. 2 is in common, 3 is in both, 4 is in both, 5 is in both. Okay, so the only ones that aren't in both 6 and 7. Otherwise, we've got both blue and green going on. So the regions that we would shade for this guy are 1, 2, 3, 4, 5. Okay, now these are obviously not equal. And that's because when I was first reading this, I was thinking it said A intersect B, union, union A intersect C. Then I would get a true statement here, but since those operations are switched, it's a lot different story, and they're not equivalent. All right, let's try another one. So this number 5 from week 3 homework deals with the complement of a set. So I'm going to start with the right-hand side, the set on the right-hand side, because it's a little bit easier to wrap your head around. So I'm just going to look at A complement. So this means basically take your universal set, which is represented by the rectangle here, and remove A. So with A complement, we're going to get regions 3 and 4, because those are the only regions that A does not happen. Okay, so A complement contains regions 3 and 4. Okay. Now let's see, if I'm looking at A union B complement, the complement of that union A complement. Okay, let's just break this down step by step. Let's start by looking at A union B complement. So what A union B complement means is to take everything in A, so take regions 1 and 2, and also take everything in B complement. So B complement is just everything outside of B, so it'd be regions 2 and 4. So if we're uniting these, we're going to take everything in both sets. So in A union B complement, I would have regions 1, 2, and 4. However, what we're asking for is the complement of that set. So we're saying take A union B complement out of the universal set. What do you have left over? So now what we're going to do is take out regions 1, 2, and 4. And if we take out those regions, the only one we have left is 3. So the complement of A union B complement is going to be just region 3. So A union B complement is going to be just region 3. Okay. Now I want to unite that with A complement. So A complement just contains everything outside of A. So I'm going to have region 4 and region 3. Okay. So A complement is region 3 and 4. I'm uniting these two sets, so when I look at A union B complement, complement, union A complement, I'm going to get regions 3 and 4. Okay. And I get the same thing on both of them. Okay. So this is true. Now let me look at one more thing here. I want to apply the properties of the complement of the union and think about it that way, okay? So A union B complement complement, union A complement. I'm going to rewrite this. The complement of a union is the complement of both pieces and the intersection of the complements. Okay, so I've got I've got A complement intersect B union A complement. So this kind of looks like that absorption law, but we can keep going here. So let's distribute this. So I'll have A complement union A complement intersect B union A complement. So I've got A complement intersect B union A complement. So it's kind of like the absorption law with logic, but not sure if that helps at all. But if I think about what's going on in here, B union A complement is only going to contain stuff all of B and all of A complement. So if I intersect that with A complement, I'm only going to have A complement left, right? But I know that all of A complement is over here, so if I intersect it with A complement, I'm going to just get A complement back. So it makes sense that these two sets are equal. Try to convince yourself, think about that absorption law for logical operators. All right, we talked a little bit about this on the Q&A session on June 10th, I believe, but I'm just going to go through and work out this problem. So we're looking for subsets of this universal set, and we want to have we want to build these sets so that any two sets have a cardinality of 2 and the intersection of all three sets have a cardinality of 1. So there's a lot of answers for this problem, so it's not necessarily the case that if your answer is different that you're wrong. As long as it satisfies the condition of these cardinalities, then you're fine. You want to work from the inside out here because we want to figure out what the element is that they all have in common, and then figure out what B and C have in common, what A and C have in common, what A and B have in common, because that's going to set some specific restrictions on A, B, and C. Because we can't add in other common elements because it'll mess up these cardinalities. So we're going to make sure that these conditions are satisfied first and then work outside to build A, B, and C. So starting here, the intersection of all these three sets has to be just one element. So they have to have all the same element or only exactly one of the same element. So if let's say A, B, and C all have the element 1. Now, we can't have any element that occurs in all three sets, otherwise it'll mess up this cardinality of the intersection. So I can't put 2 in all of them. I have to just the one element. And just so that that's not confusing with the 1 and 1, let's just say it's 2. 2 is the element that they all have. Okay. Now, I want A and B to have exactly 2 elements in common. So they already have 1 element in common because they have 2 in common. Now I want them to have 1 more. So let's say 2, 3. Okay. And now I want A and C to have 2 elements in common. A and C currently have just 1 element in common. So if I want to add 1 more, now A and C have 2 elements in common. Now I want B and C to have 2 elements in common. Now I can't put B as 2, 3, 4 because then A and B would have 3 elements in common and not 2. So I need to pick an element different than 5 or different than 4 to put in both B and C so that it doesn't mess up the cardinality of A intersect B. So now I've got, let's just check. I think that I've satisfied all the conditions with these 3 sets here. Let's check. A intersects B intersects C. So this means any element that all 3 sets have in common. So that only includes the element 2. So the cardinality of the intersection is 1 because there's 1 element. Now let's check A intersect B. What do they have in common? A and B have just 2 and 3 in common. So the cardinality of that intersection is 2. Now A intersects C. What do those 2 sets have in common? Well, 2 and 4. So they only have 2 elements. The cardinality is 2. We're good. B and C. What do B and C have in common? 2 and 5. So the cardinality of that intersection is 2. So these 3 sets satisfy the condition. Notice we could add more. We could add 7, 8, 9 here, but you can't add 7 more than one place. So you could add in the other 4 elements to these sets if you wanted. You don't have to. Actually, you can't. No, you could, as long as there's not overlap. You could do 6, 7 here, 8, 9 here. Okay. You do 6, 7, 8, 9, and all of A, and nowhere else. Okay. There's a lot of solutions. See if you can play around and find some more. But we don't have to include everything in the universal set in these 3 sets. It's okay. It could all live on the outside. So this satisfies the conditions. Alright, so now we're given some specific numerical information about a class of 30 students. So it looks like we are looking at 2 sets. We've got students who took a mathematics class and students who took a physics class. And so we need to kind of fill in these sets and try to understand the regions that are being described by each of these numerical statements. So let me write M is the students who took math, P is the students who took physics. So M means the set of all students who took math. And P is the set of all students who took physics. Okay. Now, let's try, and our universal set, right? Universal set is just the set of all the students in our class. Set of all students in a class. So I know from this statement, in a class of 30 students, I know that means that my universal set contains 30 students. So I'm just going to write that down. So my universal set, the cardinality of my universal set is 30 students. So that means, let me just label these regions. Let's say label A, B, C, D. So that means if I add up the cardinality of region A plus the cardinality of region B plus the cardinality of region C plus the cardinality of region D, I'm going to get 30. Okay, now I know that 26 of them took a mathematics class. So this means the cardinality of the math set is 26. We know 7 took physics, so the cardinality of physics is 7. Now, 3 took neither math nor physics. 3 took neither math nor physics. So that means they live out here, math, so not math and not physics. The cardinality of that is 3. So that means the cardinality of, and let me just go ahead and label this, because if you get to a number that only pertains to one region, you can go ahead and fill it in. Okay. So what the question is asking for, how many took math and physics, that would be this intersection region A here, where we'd have math and physics. And we have to do a little bit of different work here because we don't know any specific region cardinalities for A, B, and C. We only know M, P, and how many live out here. But if there are 3 elements outside of M and P, then because the cardinality of the universal set is 30, we know that 27 students must live in the union of M and P. So I know that, here, this is what I'm saying. I know that if I take the union of M and P and add the complement of that, so anytime I take a set plus its complement, the cardinality of a set plus the cardinality of its complement, I'm always going to get to the cardinality of the universal set. Now notice, this is just M complement intersect P complement. Okay. Now I know the cardinality of the universal set is 30. I know the cardinality of this intersection is 3. So now I know the cardinality of the union of 2 sets is going to be 27 if I subtract 3 from both sides. All right, now I know the cardinality of the union and the cardinality of both of these 2 sets. So what I'm going to do now is use the Inclusion-Exclusion Principle. So this means to find the number in the union of 2 sets, I'm going to take the number in both sets, but then subtract the number of elements in the intersection because I'd count those twice with counting M and P. So now if I fill in this information that I know my union contains 27 elements, I know M contains 26 elements, I know P contains 7 elements, but I don't know my intersection yet, but I'd like to know because what I'm looking for is how many took both math and physics. So that's exactly what I want to know is M intersect P. So 27 is equal to 26 plus 7 is 33, right? 33 minus the intersection. So if I subtract 33 from both sides, I'm going to get 6, right? Negative 6 is equal to negative cardinality of M intersect P. So that tells me that the cardinality of M intersect P is 6. Now let's just fill in these cardinalities just to make sure that everything's making sense. So this is saying that the cardinality of that intersection there is going to be 6. So 6 students took math and physics. Now since the number of students who took math is 26, there must be just 20 students in this region of just math. So 20 students took math but not physics. Now since the number of students who took physics is 7, then there must be 1 student over here who took physics but not math. So if I add these up, I should get 30. So 20 plus 3 is 23, plus 6 is 29, plus 1 is 30. So all checks out. And we're good. So the answer to this question, so the cardinality of M intersect P is 6. So I'd say 6 students took math and physics. All right, kind of a similar question here, but now we've got 3 sets that we're dealing with. So instead of just math and physics, and instead of just 30 students, now we've got 110 students, and we're looking at physics, math, and biology. So let's just go ahead and label our sets in our Venn diagram to better understand what's going on here. So we've got our universal set, which contains all college freshmen. We've got math, we've got physics, and biology. So let's see, universal set is all college freshmen at a particular school, right? And math, all students taking math. Or who took math, right? Because they're talking about high school. Who took math. And B is going to be students who took biology. and P is going to be students who took physics. Okay, and let's see, now we know some things about the cardinality of these sets. So let's just go ahead and break down the information we know in terms of cardinality. We know we have 110 college freshmen, so the cardinality of the universal set is 110. I know that 25 took physics, so the cardinality of the set containing students who took physics is 25. The cardinality of students who took biology is 45. The cardinality of students who took math is 48. The cardinality of students who took physics and math is 10, it looks like. And the cardinality of students who took biology and math is 8. The cardinality of physics and biology is 6. And the cardinality of physics, math, and biology is 5. And this is really the key here, because notice all these other set cardinalities that I'm given are touching more than one region. So we don't know, like for example, the cardinality of the students taking physics. We don't know how that 25 is divided up amongst these 25 or these 4 regions. We can't just divide it evenly, by 4, as that doesn't make any sense, and it's not divisible by 4. And so what you have to do is work from the inside out. So P intersect B intersect M only touches one region, this very center region here. So then I know something about this region. If I have something about the intersection of two sets, I'm just looking at 2 regions here. So if I know how many is in here, I can subtract this one to get this guy. So, and then you just work from the inside out. So let's see. So in this intersection of all the sets, I've got 5 students. So I've got 5 students here. And so to answer the question, how many took neither math, biology, nor physics? To answer that question, I need to know how many students are in M union P union B. So I really need to fill out all of my regions to understand that question. So it's not a waste of time to do this here. So P intersect B, that would be this region here. I know that contains 6 students. So that contains 2 regions. I already have 5 in one of my regions, so that means I must just have 1 student here. B intersect M contains these 2 regions here. So B intersect M contains 8 students. I already have placed 5 there, so I have 3 more to place in that region there. So that means they're taking math and biology, but not physics. So 3 students are taking math and biology, but not physics. Let's see. Physics and math. Physics and math are these 2 regions here. That contains 10 elements. I've already placed 5, so I have 5 more to place. So that means 5 students took math and physics, but not biology. Okay. So I've used this information, 6, 8, 10. All right, now I know the cardinality of math is 48. So that means if I add up these 4 regions, I should get 48. I've already placed 13 students, so that means I have 35 more students to place to get to the 48. So let's just check this. 35 plus 5 is 40, plus 5 is 45, plus 3 is 48, so that checks out. Okay. Now let's look at B. B should contain 45 elements. I've already placed 3, 5, 9 elements, so this means I should have 36 out here. So this is saying they took biology but not math and physics. So they took only biology, not math and physics. Well, not only biology, but they took biology but not math and physics. So let's just check. We've got 36, 37, 42, 45 in the set B. So now let's look at students who took physics but not math and biology. So not math or biology. So physics should add to 25. I've already got 11 placed, so I have 14 students who took physics but not math or biology. So let's just check. 5 plus 5 is 10, 11, 25. All right, so now there's only one region that doesn't have a numerical value for the number of students that live there. And actually that number is what we're looking for here. Who took neither math, biology, nor physics? So to figure this out, we need to add up all these regions and figure out how many students of the 110 haven't we placed in any of these regions. So let's just add up these numbers. We've got 35, we've got 36, 14, 5, 5, 1, 3. So let's see, make sure I've got them all there. 35 and 5 is 40, 36 and 14 is 50, 90, 95, 6, 99. 99 students. Let me make sure. 10, 14, 50, 64, 99. Okay, yeah, 99 students. So that's how many. So this tells me that the cardinality of M union P union B is 99. So if I'm trying to say not math, not biology, not physics, that's actually the complement of the union of these three sets. And the reason is just because of De Morgan's law. So we've got M complement intersect P complement intersect B complement. So I know that a set plus its complement is going to give me the size of the universal set, because no matter what element I choose, it's going to live in a set or its complement. So if I add those two up, I get to my universal set. So I know that there's 99 in the union of all the sets, and I'm trying to figure out who didn't take math and didn't take physics and they didn't take biology, and I know that should be 110. So if I subtract 99 from both sides, I'm going to find that the number of students who didn't take math, didn't take physics, and didn't take biology is 11. So that means that there is 11 out here in this region. So this means that 11 students took neither math, biology, nor physics. So that concludes the set portion of this assignment. Come back and I'll talk about the rules of inference.